All right. So in this short lecture today, let's talk about what is asymptotic analysis and what's the word asymptotic in the asymptotic analysis really stands for. So almost everyone's familiar with the asymptotic notation, the big O notation, big omega, small omega, etc. And yet the question can sometimes come, what is the word asymptotic? What does it really mean? So the word asymptotic comes from the Greek word asymptotos, which means not falling together. And the word asymptotos essentially is just a word that has the a prefix, which stands for the negation. That means not symptotos. And symptotos essentially comes from the word sympto, uh, and the tos suffix stands that it's an adjective, right? Now, the word sympto, you can easily guess some of the other English words that come from it. Symptoms, symbiosis, etc. All of them come together, as we can guess that the word sim essentially means to say together. So in this case, asymptotos essentially means not falling together, not coinciding. And yet, what does that have to do with math and computer science? So in mathematics, the asymptote is a line that a curve approaches but never really reaches. So in the context of asymptotic analysis, functions are often compared to these asymptotes to understand their long-term behavior. So what again is an asymptote? So when we are considering the analytical geometry, an asymptote of a curve is a line such that the distance between the line and the curve approaches zero as the x and the y coordinates, generally the x in our case, tends to infinity. So in projective geometry and related context, the asymptote of a curve is a line which is tangent to the curve at the point in infinity. Make sense? So let's suppose we take a little graph perspective here. When we have this n increasing from 10 to 120, the f of n could be going a little bit higher, a little bit lower, and then a little bit lower again, going higher. And then essentially it stabilizes to a larger values here. And this is the behavior of the function that we are really interested in studying, not necessarily the small deviations at the lower values of n. And that's the reason that the asymptotic analysis essentially is the analysis of the rate of growth of a function, and asymptotic notation that we use compares the rate of growth of two functions. Now the functions again can be smaller or larger, but we're trying to determine which function grows faster than the other. And if one does, then we call it the big O. The smaller function we call the function that's growing less fast than compared to the other one, we call it the big O. Small o if it's strictly growing slower, etc. So that's the asymptotic notation that we are usually interested in. If we take another example here, let's suppose we have f of n is equal to 83n squared minus 47n plus 4. So when we look at the asymptotic perspective, now that we have a little bit more understanding the word asymptotic, the lower order terms, negative 47n plus 4, don't really play any real role. For that reason, such a function can be often simplified to 83n squared, and then in fact even just to simply do n squared, because that's just a constant which we can attribute to the machine speed, etc. Rather, the n squared function already encompasses the rate of growth, and that's what we are really interested in. So that's pretty much on the word asymptotic. It's all Greek, but I think we like it.